want to talk about creatine homeostasis in kidney disease. And as many of you will probably know, creatine and kidney, for many people, it seems like a bad combination. And hopefully today I can talk to you and show you why it would actually be a good combination to have creatine supplementation in kidney disease. We haven't done really many clinical trials yet, but I want to focus mostly on the observational data to get the rationale for a clinical trial. There is a pilot that has been finished, but Siska will talk after me about that study. And I will first give a broad introduction about what we have done so far. So when we talk about kidney disease, we usually mean chronic kidney disease. And this is a major global health burden around the globe. And roughly 10% of the patients have a chronic kidney disease. And the main goal is to prevent further progression of the disease and prevent morbidity and mortality, which as a consequence means that over time, even though the incidence rate is roughly the same, there is an increased prevalence of patients with kidney disease. So this is a group that's continuously growing, mostly due to better access to hemodialysis, kidney transplantation, and that makes it an important group. And if we then look at CKD, it's mostly diagnosed by either protein in the urine or, as mostly done, an eGFR, an estimation of the glomerular filtration rate. And as many of you will know, the estimation is almost always done based on serum creatinine. And serum creatinine is often confused with creatine, and if people think creatine, they will always think about creatinine and think high creatinine means bad kidney, which is actually sad. And there is, of course, a link. Daily, 1.7% of your total creatine pool is converted into creatinine and excreted in the kidney. And one of the things about creatinine is that it is freely filtered. It is not reabsorbed, unlike creatine, which is heavily reabsorbed in the kidneys. There is some secretion, but it is negligible if you have a normal kidney function. And that actually makes it a pretty good marker to assess the kidney function. In general, you can say the lower your kidney function is, the more you will accumulate creatinine, and thus you have a higher serum creatinine. And that's why it's used almost, even though we have other markers, it's almost in clinical practice always this one that's being used. And sadly, that has led to the belief that a high serum creatinine is always bad. But serum creatinine is not just defined by its elimination, it's also defined by its production. And the production depends on your total creatine pool. And if you say total creatine pool, we can also say muscle mass, because almost all of your creatine, over 90%, is in the skeletal muscles. So that means actually if you have a higher muscle mass, you will also have higher serum creatinine by default. And if you would only look at serum creatinine, you would say, oh, your kidney function is bad if you have a high muscle mass. So to adjust for this, we use different equations, and all those equations try to adjust for muscle mass at a population level by using age and sex to determine, to adjust for your muscle mass. And in general, those work pretty well if you have a normal muscle mass, and if the loss of muscle mass over time is equal to the age-related loss of muscle mass. But as you can imagine, that's not always the case. Here are some equations. But that's not all that important. What's important is the higher your muscle mass, the higher your plasma creatinine, which may falsely imply that you have a lower eGFR. And that's especially important if you have a patient that you are following up over time and he's losing muscle mass every year and it's more and more. Then you will, if you only look at your serum creatinine-based eGFR, you get an underestimation of the actual eGFR. It also makes it difficult to study anything related to creatine using the creatinine-based eGFR, because if you give creatine supplementation, you can increase your total creatine pool and also increase your serum creatinine and think it must be bad for the kidneys because serum creatinine is going up. Of course, that's not truly the case. So actually those eGFR estimations based on serum creatinine are not valid if you have not a stable or normal muscle mass over time. And one of the big problems is, of course, that in many diseases, the case is that diseases tend to affect both kidney function, but also your overall muscle mass. And your kidney function on its own can affect your total muscle mass by their effect on creatine synthesis. So it's a complicated triangle, which actually makes it, when you're studying muscle mass changes or studying creatine, it's better to always use a muscle mass independent marker to estimate the GFR. And one of those is cystatin C, which can be used. But in clinical practice, it's still rarely used, unfortunately. So what we have here is maybe a little difficult graph, but I just want to focus on one part of it. Let's see if I can point. Yeah, on the left part, and here we have data from a large general population cohort. So these are not sick patients, But we've divided the general population cohort of roughly 6,000 patients into groups that are stable in muscle mass, losing muscle mass, or gaining muscle mass. And on the left, you see the patients that are losing muscle mass. And in yellow, you can see the estimation based on cystatin C, and in blue, on creatinine. And then we also have green for the combination, the combined equation. And as you can see, if someone is 50 years old and they start to lose muscle mass over time, then over the years, there will be a divergence of those eGFR equations. And for a 50-year-old with the equation, the difference seems, there's still a big difference, but it doesn't seem that impressive maybe. But if you look at someone that's 70 years old, you can see that the difference is huge. And it's even so big that a healthy person that starts at a normal eGFR, over a follow-up of 15 years, might develop CKD, which you would not detect if you use your creatinine-based eGFR. So that's just to show how important, especially for older people who will lose more muscle mass and who will also be more at risk for CKD, so it's actually the most important population, that it's not always valid. And that's why one of the reasons why for the studies that I will show next, we always used cystatin-based eGFR when we study the relationship with muscle mass or with creatine pools. So in simply put, you get an overestimation of your eGFR if you lose muscle over time, and you get an underestimation if you are gaining muscle, or for instance, giving supplementation. And the alternatives are the cystatin C-based eGFR, but you can also do a creatinine clearance in which you adjust for the creatinine excretion, which is a measure of your creatine pool. Or even better, but it's a little bit more invasive, so it's not used that much, use a measuring of the GFR using iodotalamate. So unfortunately, in nephrology, many researchers are not looking at creatine at all. And it's very sad, but it's mostly due to misconceptions. Because creatinine sounds like creatine, people think creatine supplementation is bad for the kidney. Based on a few sole case reports in which they did not look at a true marker of eGFR, or in which there was concomitant disease or anabolic steroid use. These are all separate case reports, but those have done so much damage to the misconceptions that there's very little research in nephrology on creatine. Creatine is harmful to people with kidney disease, also something that's being said a lot, even though there's no data to actually support that. Or high creatinine is always a kidney problem, and it can be a kidney problem, but it can also be supplementation or an increase in muscle mass. And actually what you should want for patients with CKD is an increase in muscle mass, because muscle mass, it doesn't matter at which population you look, muscle mass is one of the, and most often the best predictor for survival in patients with kidney disease. And we've seen that in hemodialysis patients, kidney transplant recipients, and also even in the general population at risk of CKD. So like I said, those ideas have stunted research, and many, even nephrologists who you would think would understand this idea and this conception, they are also very reluctant to go into research on creatine. So I won't go into detail too much about this, but if you have your creatine pool, which is mostly in your muscle, then it's under a lot of stress, because every day you're losing 1.7% roughly to conversion to creatinine, which is then excreted in urine. Which means that if you want to maintain a steady state, every day you need to have a continuous supply of creatine. And that can be a production that you have endogenously, for instance, the synthesis steps, but it can also be dietary intake. And you can imagine if you have a lower production, you need more dietary intake, or vice versa. So at some point we were thinking, what if the kidneys are important for that first step, and that's something what has been debated about. Originally the thought was the kidneys are the main site. Now later people also found AGAT expression in other tissues like the pancreas or, well, more. But if the AGAT is mostly in the kidneys, then you would imagine if people get CKD, then over time, the more they advance, their endogenous production will go down and down and down until you have dialysis at stage 5, and you will have basically no kidney function anymore. So no filtration, but also no synthesis capacity, or at least very little. Then that means at the same time, if you want to maintain a steady state, you need to eat more creatine every day. But the thing is, patients with advanced kidney disease, even though it's not completely in all the guidance yet, they get more and more the advice to eat plant-based foods because it has more fiber in it, more antioxidants, less phosphor loads, less protein. And yeah, in reality, that means that if they progress more and more, they actually don't increase, the demand will increase, but they don't tend to increase their creatine intake at all. And none of them even take supplementation because many of their doctors will say, stop taking creatine supplementation, I can't look at your kidney like this. And we think maybe that could be one of the reasons that many of these patients suffer from complaints related to creatine, like a loss of muscle mass, which we see a lot in nephrology, and fatigue, also one of the things you see a lot happening if people advance from CKD 1 to 5. So when we hypothesized this, we realized that Theo Walliman and Uwe were actually having the same idea. And we got in contact with them, and they told us how difficult it has been for them to find someone in nephrology to even consider the idea that creatine might be not bad or even good for patients with dialysis. So we started working together, and today I want to talk a little bit about the 3 different populations to show some evidence why it might be a good idea to start creatine supplementation, and then Sietske will talk about the pilot we did in dialysis patients, because dialysis patients is the most vulnerable group. So for the dialysis group, we made an observational biobank from roughly 60 people, and we collected plasma, urine, and dialysate. And that was not easy because the dialysate production in one dialysis session is roughly 120 liters. So if you want to collect that, you have to collect it all and then homogenize it to get samples. So even though we only used like 20 milliliters of samples, we had to collect 120 liters for every patient all the time. We started out like this with a little box, but then we realized, yeah, not everything is stable if it's at room temperature. And we wanted to homogenize it in line, so we actually upgraded it later to this, which had a cooling unit in it and homogenization in line, so we can use it more and more. But as you can imagine, it also gives analytical problems because you have a very, very diluted matrix, because many analytes in it will be very diluted. So we also had difficulty measuring every substance we wanted. And the problem with plasma values is that the plasma values from dialysis patients are never in steady state. They're always going up, accumulating, because they have no kidney function. And then there's a bout of removal during the dialysis, and then they go up again. And there is some form of steady state in the sense that if you collect everything in one interval, it will be the same in all those intervals at some point, because they go 3 times a week. So you can get some measure of steady state. So to do that, we measured urine collection in this, if they were still urinating. Some of them do, but many stop as soon as they start dialysing. And we collected plasma values here and here, or actually here and here, but it's the same. So we get an idea of how is the plasma concentration roughly, but somewhere the true steady state will be somewhere in the middle. And you can actually calculate your excretion as well if you use the urine collection during the interdialytic and the dialysis collection intradialytic. And you can calculate a excretion. So we measured arginine, guanidino acetate, creatine, and creatinine in all those samples, and we had questionnaire data on fatigue. We also looked at mortality, but as you can imagine, 60 patients, very low sample size, even lower event rates, even though many do tend to die quickly on dialysis. And I have some baseline characteristics, but in general, it's just a regular dialysis cohort. And what we first looked at is how are the plasma concentrations? And here I have the concentrations before dialysis and after dialysis. And for guanidino acetate, we saw that the concentrations were actually much lower than in the healthy populations. We had another cohort as a control, and they were roughly 30% lower in healthy males and 20% lower in females. And that's comparing against the highest values. And you would actually expect that dialysis patients have much higher values than lower values if synthesis was not impaired, because you have no kidney function, so you accumulate and you accumulate. But instead they were lower, which does seem to indicate that the endogenous synthesis is indeed impaired in these patients. If you compare against the post-dialysis values, the difference was much larger. Then we looked at the creatine samples, and we saw the same. We saw there's much lower values compared to healthy males, roughly 40%, and in females it was 20%. And what's also interesting about this is that the plasma concentrations of creatinine were higher in females as compared to males. So that's something we see in all the cohorts where we study it. It's always higher in females. And what's interesting to see here is that if you look at, and actually the same was here, if you compare it against post-dialysis values, it's even lower. But if you look at how much people decrease in creatine, it's actually not all that much. In males, there's very little decrease during the dialysis. And in females, there is some decrease, but it's much less than the removal from, for instance, creatinine or from guanidino acetate, in which you drop 40%. So that got us thinking, like, is it not being removed during the dialysis? Does it not pass the filter or anything? Or is it regulated tightly so that the body prevents the values from dropping all that much? So luckily we had those dialysis samples that we collected. And here we could see that it is indeed being removed. And we saw that the total losses were roughly around 700 micromole per dialysis session. But if we then calculate using extracellular volume estimations, how much is lost from which compartments, then we see that most of the losses is actually not from the extracellular compartments, of course, because the plasma values stay roughly the same, but it's actually the losses are mostly from the intracellular compartments. But this actually does mean that there is removal during every dialysis session, so it's only a matter of time, if you don't start eating more creatine, that you will get depleted over time. So next, we wanted to look at the logistic regression with outcomes. And we first looked at arginine and plasma glucosinolacetate, and we saw actually not many relationships with outcomes. We did see some point estimates that were higher, but it was all not significant. It is a small sample size, so of course that could play a role, but if we look at plasma creatine, which we defined then per halving, so log2 transformed, because it was very skewed, then we see that for every halving of your plasma creatine, those patients had a much higher odds of being in the group of having a low muscle mass, of having a low protein intake, of having a low serum albumin, not an effect on BMI, but as we heard previously, that's not all that important. And very importantly, we saw that they have much more fatigue. And fatigue is especially of importance in this group, because many dialysis patients in questionnaires have said they would be willing to accept more dialysis, more frequent, for less fatigue, but they would not be willing to accept that for a longer life, because the quality of life is so impaired by fatigue. So the fact that we saw this effect on fatigue was actually very strong and very interesting to see. And here we can see it again in the graphical format, but in general, the lower your plasma creatine, the more it was associated with poor outcomes. And low muscle mass, low protein intake, and low albumin, those are part of the protein energy wasting syndrome, which is important, which is actually simply said sarcopenia in kidney disease. And plasma creatine was interesting for us because it's so important for patients from their patient perspective. We did also look at mortality data, but we had very low sample size, like I said earlier, and plasma creatine was not associated with mortality. But like I said earlier, you can actually get an estimate of the creatine pool if you calculate the urinary and the dialysate creatine excretion combined, and then calculate it back to the daily losses, because there is some form of steady state over every session. So when we did that, we saw that the patients that died, almost all of those that died, and even though it was only a few, they were all in the ones with the lowest creatine pool. So then the question, of course, is, what does this reflect? Does this mean that, like I said, most of the creatine is in muscle? So that's a difficult question always. Is this just a reflection of a low muscle mass? Or is the creatine pool of importance? And it's always difficult to have a distinction there, but it was definitely interesting. And it could, of course, be both. So if we conclude quickly our small study on dialysis patients, the plasma values of glucosinolacetate and creatine were much lower. The creatine is removed by hemodialysis, and we see a large shift from the intradialytic shift from the intra to the extracellular compartments. And we see that lower plasma values are associated with higher odds of low muscle mass, low protein intake, and especially fatigue. So we think over time they will deplete their creatine stores, especially if they don't start eating more creatine. And that was actually the rationale to have a trial in which you do an intradialytic creatine supplementation. And Siska will talk more about that, so I won't go further into that topic. But next, we wanted to get some more data on what's happening in a non-hemodialysis patient group. So for this, we used the PREVENT cohort, which is a study in Groningen in which they wanted to investigate the risk factors for developing CKD over time. So it's a population, it's a general population, but it is enriched with microalbuminuria. And what we did here is we wanted to make a difference between is muscle mass important or is total creatine pool important. So we tried to estimate the intramuscular concentration of creatine. And like I said earlier, the creatine pool, if it is daily having a removal of 1.7% to creatinine, which is then excreted in the kidneys, then you can calculate back what your total creatine pool is by dividing the urinary creatinine excretion by that number of 0.017. For accuracy, we performed 2 separate 24 urine collections with strict instructions. And we also assessed muscle mass using a different method. And for this, we used a bioelectrical impedance analysis. So we have creatine pool on the one hand and muscle mass on the other hand. And if we divide those by each other, we can have an estimate of what the intramuscular creatine concentration must be. And using that, we can also look at plasma creatine and calculate the gradients over the muscle cells. So first, looking at plasma concentration, we see the same trend we saw earlier. Females have a higher plasma creatine as compared to males. And we didn't have data on, we didn't have full data on sex hormones or anything, so we could only look at whether or not they were post or premenopausal. And strangely enough, in the postmenopausal women, they actually had higher creatine than lower creatine. Unfortunately, we couldn't further investigate that because the cohort wasn't designed to have more data on this topic. But it is the same as we saw in the dialysis patients. Again, higher in females. And interestingly, if we look at linear regression analysis, we see that the higher your, the blue box should be one lower, and the EGFR, the higher your kidney function, the higher your plasma creatine. I'm starting to say it wrong myself. And what was especially interesting and completely contrary to what we expected is that high plasma creatine was associated with traditional risk factors in a positive way. So patients with higher plasma creatine actually had more cholesterol, had higher triglycerides, higher glucose, and there was a strong interaction in those associations, which were mostly present in males. So when we looked at outcomes, and we had outcomes like mortality, but also hypertension and diabetes, we saw that actually plasma creatine was associated with hypertension and diabetes in the way we would not expect it to be. A higher plasma creatine was associated with both higher incidence of diabetes and hypertension, but only in males. So that was also very strange and contrary to what we expected. So we wanted to next investigate, like, is plasma creatine actually a reflection of what's happening intramuscularly, or is it something different? For instance, lysis of erythrocytes, or a sign of muscle breakdown. Because you can imagine if the gradient is very high, if there are cells lysing, then creatine in plasma will largely go up in patients, and it will then be it will explain why it would be a bad sign to have a higher plasma creatine. So if we look at the intramuscular creatine concentrations, we can see the same trend. They are higher in females as compared to males, and it was not such a big difference as for plasma creatine concentration, but still it was higher, and this is in line with biopsy data, where they found roughly 10% higher plasma creatine concentrations in the muscles of females compared to males. And if we then look at the gradient, it's higher in males. So, like I said, we wanted to see, is there a correlation between the two? And actually there was quite a poor correlation. As you can see here, it was significant, but it was significant because we had 6,000 patients, so it's not that hard to get a significant association. But if we look at how much of the variation in your intramuscular creatine is actually explained by plasma creatine, it was quite low. Even in a multivariate model, it was less than 5%. So actually that made us to believe that plasma creatine is probably not a great reflection of your intramuscular creatine, at least in the general population. It might very well be in dialysis patients, where we did see the associations. And it could very well be that, that it's only a reflection of the intramuscular compartment if the system is very stressed, like in hemodialysis patients. So if we then look at associations of both, we see that with age, the intramuscular creatine concentrations decrease, while the plasma creatine concentrations are actually increasing. But both were associated with the EGFR. If we then look at outcomes, and then mostly mortality, then we see actually that the intramuscular creatine concentration is very protective against mortality, even in a non-sick patient population. These were just patients at risk of CKD. They did not have any damage yet. But still, we see that the intramuscular concentration was a very strong predictor for mortality. And this is during a follow-up of 17 years with many events. And this remained significant after adjusting for multiple potential confounders. And strangely, here we see that intramuscular creatine is actually protective in females and not so much in males, which we can also see in the next graph. This is from the multivariable adjusted model, and you can see that there is an association in the full group, but it is mostly driven by the effect in females, where the intramuscular concentration is most protective against mortality. So to summarize so far, in both these cohorts, plasma creatine is higher in females as compared to males, and plasma creatine may not fully reflect your creatine in the muscle compartments, at least not in circumstances where there's not a stress on the system, so to speak. Because in a dialysis patient, we see that low plasma creatine is actually unfavorable and associated with worse outcomes, while in the general cohort, we see that the high plasma creatine was associated with more traditional risk factors and with hypertension and diabetes. But a higher intramuscular creatine concentration was very protective in the general population. And we unfortunately did not have that data in the dialysis cohort because we had no second muscle mass assessment than the creatinine excretion. So next we wanted to investigate it further in a different population, a population that has CKD, but has a wide variation in kidney function, because these were healthy patients, so the kidney function range was quite low. So we looked at kidney transplant recipients, which is also nowadays the gold standard treatment for end-stage kidney disease. And like I said, more and more people are going to be kidney transplant recipients because it's the gold standard for treatment, and we are trying everything in our power to have those patients live longer with a graft. And it's a good population to study those associations because they have a large variety in the kidney function. So first we wanted to make a comparison with controls, and for controls we used the kidney donors, and the kidney donors are a very healthy population because they are screened to be healthy, and they can then, we made a comparison, and second we did an analysis similar to the one we did we did before, and I'll try to go through it a little bit faster because I don't have that much time left. So what we did, we made a comparison. The main difference between the controls and the kidney transplant recipients is the lower kidney function. What we saw was actually that the creatine pools, the total creatine pools, were 13% lower as compared to the controls. However, if we look at the dietary intake, which we assessed using food frequency questionnaires, we see that the dietary intake was similar between the groups. And if we then look at what is the endogenous creatine synthesis rate, which we can calculate as the urinary excretion of creatine and creatinine combined, minus the dietary intake of creatine, there was also, of course, the intake of guanidino acetate, but that was very low. And we see that the endogenous creatine synthesis rate in kidney transplant recipients is actually 22% lower. And we also looked at a lot of plasma values and urinary excretion, but I'll skip this real quick. What we looked at is how is the association of the endogenous creatine synthesis rate and the total creatine pool with muscle mass, with kidney function. And for this, we used a subset of patients who had MGFR data. So this is the most true form of measuring your kidney function. You actually give patients an intravenous infusion and then measure the kidney function. So this is the most reliable method. And we saw that in kidney transplant recipients, but not in controls, the kidneys are very important for the endogenous creatine synthesis and for the total creatine pool. And interestingly, even though the sample size is the same, these associations were not found in controls. So it seems that the kidneys are more important for creatine synthesis when the system is under stress, like in the kidney transplant recipients, but not so much when you're healthy and perhaps the pancreas or other tissue can take over. And we also saw that the association was very strong for guanidino acetate excretion, which can be seen as a rate for the first step, because the guanidino acetate is the first step of the two-step synthesis process. So we did a quick mediation analysis, and what we actually see, and I'll go through it a little bit faster, but we see that the full effect of the association between the measured glomerular filtration rates and the endogenous creatine synthesis was fully explained by the urinary excretion of guanidino acetate. So that actually supports the notion that CKD leads to reduced creatine pools because insufficient synthesis of the first step product, the guanidino acetate. So for the second part, we did the same analysis that we showed earlier for the prevent cohort, and we can see the same trends again. Higher intramuscular creatine concentrations for females, higher plasma concentration for females, and a higher ratio for males. And we also see again that the intramuscular creatine concentration decreases with age, is positively associated with kidney function, but also interestingly, is decreasing the longer patients live with a graft. So that also means that the longer you have a kidney transplant graft, the more your creatine synthesis starts to decrease over time. I'll skip this one, but shortly put, the higher your plasma creatine, the higher your intramuscular creatine, the less fatigue. So the same as we saw in the dialysis patients. But when we look at mortality, we see again the same associations. We see that intramuscular concentration of creatine is very protective against mortality. And this effect is mostly driven by females. But interestingly here, it is also borderline significant for males, because probably this is a more severely impaired patient population. And here we can see it again. So to summarize this, compared to the controls, the kidney transplant recipients have lower creatine synthesis, they have lower creatine pools, And the kidney function, which we had a large variation of, we could see that the kidney function was strongly positively associated with your creatine synthesis, which supports the notion that creatine synthesis is very dependent on kidney function in this population. And with regards to outcomes, higher plasma concentration was associated with less fatigue, but higher mortality, whereas a higher intramuscular concentration was strongly associated with less fatigue and a lower risk of all-cause mortality. So overall, to summarize everything together and all the populations, well, we realized when we have to study anything related to creatine and kidney function, we have to use a muscle mass independent marker of the kidney function, which could be cystatin C based, for instance. And lower plasma creatine was associated with more fatigue in the general population. And in less severe CKD patients, there is no association between plasma creatine and intramuscular creatine. But regardless of where we look, we see that the higher intramuscular creatine concentration is beneficial. And hemodialysis patients, like I said, are the most vulnerable patients. So this is the first target population that we had for a supplementation study. But pending those results, we could also have a good rationale to start with supplementation of kidney transplant recipients. So that was all. Thank you.